Okay, hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engine, no libraries, it's just our code here, and this is an educational stream, obviously. It's a way for us to take a look at absolutely everything that goes on when a game is actually running. So including the engine, including what the graphics card does, basically everything. So we look at everything in full detail, basically try to get sort of a holistic view of how game programming actually works, not just a pigeonhole thing of like how to do this one little thing. And it's been going pretty well so far. We're right in the middle of a topic that's very important for any kind of game development, which is optimization, what to do when your code is too slow and you're not getting the performance that you need. And so we're taking a look at that stuff right now. What we did yesterday was we kind of verified some performance analysis stuff by putting some performance counters in our code that tell us how long things take. And today what we'd like to do is start looking at what we can actually do about that in order to start acting on the information that we have based on the performance information that we've gathered. So I'd like to go ahead and jump into that. If you want to follow along at home, today's day 114. So if you have pre-ordered the game on handmadehero.org, you want to download day 113 source code, because that is the source code that I am starting with today. So if you want to follow along at home, please make sure you start with that. So let's go ahead and open things up. Open them up. And if you remember where we left off before, we were taking a look at draw rectangle slowly, right? And what we had is we were dumping to the debug port. You could see that we would every frame dump out some cycle counters that tell us some interesting information about our code, such as the fact that we are currently spending about 384 cycles per pixel doing things, right? And we were at the point yesterday where we want to start thinking about what is a reasonable number of cycles per pixel that we actually think we could get this routine down to. And so one of the things that we kind of need to do at this point in order to start forming that kind of an estimate is we need to start thinking about draw rectangle slowly a little more carefully, because we really were just trying to get it working when we wrote it the first time. We were just basically trying to learn how to draw texture map triangles. We didn't actually try to organize this code to be particularly optimal or to do anything particularly interesting in terms of performance. All we did was do what worked, right? And so what we need to start looking at now is, can we do some transformations on this code to put it into what we think is a relatively clean, minimal set of calculations that it's actually doing. And then we can look at that and go, with this algorithm that we have here, how many operations do we actually have to do? And that will kind of give us a little bit of guidance as to what we actually, what we can actually expect to see in terms of peak performance, which kind of gives us a goal to work towards, right? So what I actually want to do here with draw rectangle slowly is I would like to excuse me. I would like to sort of spawn this routine out, basically. I'd like to take draw rectangle slowly, and I'd like to sort of pull it out into its own, into basically a new version, right? And we'll call that draw rectangle quickly. Maybe we'll call it draw rectangle hopefully quickly, right? And we can go ahead and have that. And we're going to take that normal mapping out for the moment, because we're not going to focus on that just yet. But we're going to leave everything else in place. So we're going to do everything else in here, and we're going to have draw rectangle hopefully quickly. Rectangle hopefully quickly in here. I'm going to add a performance counter for that. And we're going to make a version of this that's just a little more cleaned up in terms of what operations it actually has to do. Let's see here, hopefully quickly. So we now we know that really this preamble here is not something that we super need to focus on at the moment. And the reason for that, of course, is that if we were to actually optimize this part that's not getting called per pixel, it would have very little effect on the performance as it is at the moment, right? most of our time we know is spent actually inside, because the performance counters are spent inside these pixel loops, and that makes perfect sense because there's just a lot more pixels than there are rectangles, right? And so you're spending a lot of time in here because, hey, there's just a lot more pixels than rectangles, so it doesn't matter what you do per rectangle, per pixels where the time is spent. Right? Okay. So what we'd like to do now is we'd like to, and I'm going to leave these time blocks for the moment to just be test pixel. Actually, because we're not going to call these. If we start calling them together, we can play with that. But I'm going to switch between these two routines, so I don't really care. So let's take a look at this. First, I'm going to go ahead and remove everything that we don't actually need in here, right? So I'm going to take out this normal mapping code, right, that we had in here, like so. Believe that's everything. And I am going to try to make sure I don't delete anything that we need. So let's go ahead and put that in there. Okay, did I get everything correctly there? Okay, there we go. Draw a rectangle slowly will be replaced with draw a rectangle hopefully quickly. And of course, this never passed any normal mapping to it anyway. When we actually just drew bitmap, that was not something that did that. So now I want to make sure that that's still running properly. It is, so that's all good. And we can see that the timing is the same, which is what we would have expected, right? Okay. So up in draw rectangle hopefully quickly, I'm going to go through this loop now and start to take a look at what it is that we're actually doing here. Right? And maybe get rid of some of the vector operations as well, just so we can really be much clearer as to what's actually happening inside the routine, right? And you can kind of see, well, you know, we've got some stuff here that's relatively straightforward. You know, we're advancing by pixels. That seems all totally fine. But inside here, where we do this stuff, and we're doing our dot products and that sort of thing, I just want to make sure that this stuff looks relatively kosher. You can kind of see in here already that there's some stuff that probably doesn't make a whole lot of sense because, you know, x-axis minus y-axis and this like negative perp y-axis, all this sort of stuff actually boils down to some pretty basic things that are going to be happening in scalar form that we could optimize out. And also even in vector form, you can see you know, x-axis and y-axis are constant. So, you know, even if we had to do it this way, you wouldn't probably in the middle of your loop constantly be doing repeated subtractions and stuff like that. So I want to take a look at this edge testing code and maybe make it a little bit more explicit, right? So if we take a look here, we've got the inner product of D with negative perp x-axis, right? And we kind of know exactly what perp does, right? If we go in here to math.h, here is perp, right? It just swaps the two things, and it swaps the two things and negates the y, right? So we actually know that the inner product of D with perp is just the same as if we had written out that inner product like this, right? So we could say edge 0 equals the inner product. And we know that A is D, right? And we know that B is just the perp of x-axis, right? So we know that this term will become negative. And here's x-axis x, right? And here's x-axis y. Sorry, y, x. You swap them, like so, right? So we know that that's actually all that was computing. And so we can kind of cut down the complexity there by just looking at that and going, OK, that's just you know, a very straightforward computation. I'm going to get rid of that. There we go. For edge 1, we have basically the same thing, right? We've got, you know what, and what's kind of interesting about these two here is you can also see there's additional kind of stuff we could take advantage of in certain circumstances, but I'll kind of leave that for later, because you can kind of see if you know that the y-axis is the x-axis but perpendicular, then when you perpendicular it again, you just get the x-axis back pointing in the negative direction, right? So you kind of have this interesting thing where you're like, okay, you know, looking at this actual value, you can kind of see where you would get some additional stuff. In fact, I'm gonna take a quick detour over here to the blackboard. I just want to kind of look and see if we really actually need to do what we're doing here with all of these inner products, actually, now that I think about it. Because if you take a look at what's actually happening here, right, we've got a vector to the pixel, right? D is a vector to the pixel. That's what it actually is, right? So that's what like D is, you know? And then we have, this is our x-axis and this is our y-axis, right? And so if we were to take D and do the inner product of D onto that x-axis, I feel like we really shouldn't have to, check all of those parameters, right? Because if we take that, that inner product, we could actually we could do something like pre-normalize that x-axis at the top of the routine and just look to see whether, you know, how far it had gone along it, right? So we could do one dot product and then just test the bounds, you know, on either side, right? So I feel like this is probably actually not the most efficient way we could actually iterate over this, you know, in terms of our equations here. And similarly, you can see right here we're computing the u and the v to do our texture mapping. And the u and the v would also tell us whether we were inside the bitmap, right? I mean, if we just ignored this edge stuff entirely, right, and didn't ever test the edges, what if we just tested, you know, tested these two, right? So yeah, I mean, suppose we were to compute the u and v coordinates and just look to see whether the u and v coordinates were actually inside the square. That seems like a pretty easy way to go, and that gets rid of all this work, right? Does that seem reasonable? So I'm just saying maybe we just do this as a test, right? Something like that. And I guess I don't know how we want to do inside outside. We'll have to think about that a little bit, like which of these it actually goes to. I'm suspecting we probably need to do it like that. But yeah. So if we were to actually do that, do we actually even need any of this, right? Could we just get rid of that entirely, for starters? So let's take a look. And hey, unsurprisingly, we did not actually need that. And our game actually got a little faster just doing that, which is kind of funny, right? You can see that it actually got, we were up at like 380 something and now we're at 303. We got a little faster just getting rid of that. Okay. So anyway, that seems much smarter anyway, because now we just have that inner product here times the inv axis length, right, which seems pretty good. But if you look at that, now that I think about it, that's actually already doing too much work too, because we could have just pre-multiplied the x-axis by the inv axis length squared to begin with, right? And if we were to do that, then we wouldn't have to multiply it every time. So that seems like a pretty reasonable thing to do as well, right? I mean, you can imagine if we did some kind of like, you know, n x-axis or something like this, which is just this times the x-axis. We should be able to replace this with n x-axis and then be done, right? v2 and y-axis equals that times y-axis, like so, and y-axis, and off we go. I don't know. Just seems pretty basic, right? Pretty straightforward. Again, everything's still blitz fine. No issues there. And just to make sure, that I didn't mess anything up. We can also verify that we are actually calling that draw rectangle hopefully quickly, right? So there we go. Right. And of course it's hopping all around because it's in debug mode, but that's fine. All right. So again, I'm just going through here. It's very simple, just pruning out stuff and getting us down to what would be a reasonable thing to even analyze, because we just have a ton of stuff in here that just doesn't need to happen, as we are finding out. So the screen space UV is not actually used unless we're normal mapping, so that goes away. ZDiff, same thing, right? I believe. Yep. So that all goes away. We now no longer have to worry about the clamping because we're actually checking to get into the loop, so that'll go away. And then we have our texture boundary multiplication. So we've got our texture width and height -2. We need to think about this a little bit. I'm going to leave that for 1 second. We've got our clamping here. We assert just to make sure that we're within range, which is fine. That'll compile out in release mode. We have our textile sampling code, which I imagine we're going to have to get a little hardcore on. We come in here and we've got our clamping. Then we do our pixel packing, and we go into linear space, do the blend, come out of linear space, and repack. So all in all, there's not a whole lot of code here. You can see it's already starting to clump down a little bit. So in order to produce this X and Y, yeah, it looks like texels. Okay, so it looks like basically what's happening here is we're clamping the RGB between 0 and 1, but unless we were going to pass in color values that were greater than 1, we wouldn't really need to clamp them here anyway. That was really for the other routine, which was potentially producing color values that are greater. We could still put a clamp in here. It's not particularly expensive to do the clamp, but what we could do instead, I'm not sure if we actually care about that clamp very much. I guess we can leave it in there, and because in SIMD it's going to be extremely cheap to clamp that, so maybe we'll leave that in just in case we want to set these color values to be able to blow things out, like set the color to be, multiplied by 2 or something like this, instead of things that always just keep it normalized, right? All right, so I'm going to go up and grab the rest of this stuff and inject it into this routine just so we can look at it, right? I want to see what it's actually doing. So here's our sRGB to linear code, right? And what that's doing is it's taking dest and it's doing that to dest directly, right? So it's basically converting dest into that space by squaring it. So we would need that IM255 to be up here. There we go. And squaring, after we do this inverse, squaring is obviously just multiplying this thing by itself again, so that's pretty straightforward. Up just one more multiply. And then, of course, this one doesn't get squared because that stays in that space. So there we go, going to linear brightness space. And then linear 1 to sRGB, same thing again. Just going to cut that out and put that in here. And again, all I'm really doing here is I'm just flattening this routine out so I can see everything it does and think about it in one place, which is just a lot easier for me than trying to go chase down a bunch of separate routines, right? So really, we've got blended here, although technically, I don't know why we even need to do that. We could just compute that right in place. I'm not sure why we bothered doing it that way, but let's go ahead and finish doing it this way anyway. Blended, blended, blended. There we go. And get rid of that. Okay. And let's take a look. Just make sure that runs. Everything looks good there. all good. And so if we take a look in here, this is a wide operation as well, as is this one and this one. We've got several wide operations here, meaning they're operating on a vector at once, right? I shouldn't say wide because we're not talking about SIMD wide. Basically what I mean is not scalar. So what I want to do is take a look at these here. 1 minus Texel A times dest plus Texel, right? So that's what's happening to dest immediately after I work with it, right? Immediately after I put it into this space. I'm essentially doing, I'm going to blow this out here into scalar form, RGB A. Here we go. Okay. So all of these have the same operation there. Oops, what did I do? Ah, there we go. Okay. So let's take a look here. I don't see a whole lot of cruft in what's happening here. It looks fairly straightforward, right? We're squaring these values to bring them into the linear brightness space, which makes perfect sense. We have to compute the Texel A, which we use. So you know we've basically got an im Texel A here, right? Which is this value. It's 1 minus the Texel A. We've basically got an inv Texel A here that we're doing to each of these. And if we were to smush these guys together, I don't see, there's really no way to get any benefit out of these. Like, I'm not seeing any way to collapse any terms here. It's all just pretty much multiplies that have to happen, right? I mean, I don't know. I really don't, I do not see anything there. What is that 1/255 bit? That's just 255. Okay. So do we know why this one was not using that value? Is there some explanation for that? Like, why did these guys all do 1/255 and this one doesn't? Know why that was. Seems a bit odd. All right. So those guys all multiply. All right. So again, no change. Everything's good. And so let's take a look up at, we probably need to start taking a look at the bilinear blend and stuff here, because it doesn't look like there's a whole lot else that we can actually focus on. So we're starting to see this code blown out to everything that it actually needs to do. I'm gonna go ahead and make this guy be more explicit as well. I'm just gonna have dest be actually written out in scalar as well. And again, this is just so I can kind of see what it actually looks like when you're not hiding operations behind a bunch of utility functions, right? So let's go ahead and make that happen. So this is us producing the, this is basically us doing the unpack, right? Dest B, dest A, like so. There's the unpack, and then we do the operations on the unpack. Now, this guy also works the same way, assuming that we leave the clamp in there. So I could turn that guy into scalar as well, and we'd basically just have these operations here where we've got Texel. So something like this. Right, Texel equals Texel R. Float Texel R equals Texel.R times color.R. GBA, GBA, GBA. All right. So that's entirely blown out into scalar now. And really the only part that we're not dealing with explicitly is this part right here, right? So you can kind of see absolutely everything that we actually need to do here in explicit form. So that's pretty good. Again, everything looks fine. No worries. So if I'm actually doing all of this stuff in scalar, what do I get when I take a look at my sRGB bilinear blend, right? My sRGB bilinear blend, it has to do a bunch of unpacks. So you can see that this is really nasty. Like, look at this guy. This is just a beast. All of this stuff is really pretty mundane. Like, you can see there's just not that many operations here. We've got them all written out. It's not that bad to deal with. But this, the bilinear blend with the sampling is just nasty, right? The actual loads are not that many operations. Of course, you know, they're probably slow because they're loads, but you can see how many operations happen here. You've got to do that unpacking. You've got to do that that sRGB to linear on all of them. And then you got to do the double lerps. It's just nasty. Nasty, nasty, nasty. But that's what we're doing. So nasty it may be, but we're going to have to actually make it happen. All right, so let's go ahead and actually paste these guys in there so we can start to look at them. Let's see here. Bilinear sample. Bilinear sample, like I said, is not that bad. Right? Taking the Texel sample is actually not that bad. So we'll do those as sample A, B, C, and D, like so, which is not too bad. And that's going to take, those are actually packed pixels that come in here, right? And then when we actually grab these out, let's see, Texel pointer, we have texture, X and Y. So they actually we're already using the variables that we wanted to use, so that's totally fine, like so. And then sRGB bilinear blend, put that guy in there. And that will just take Texel sample. So this is just going to do sample A, sample B, sample C, and sample D. And I think that's about it. And then that just produces that final Texel value. There we go. So now we have the routine semi-flattened, but we still have to look at these guys, right? And so this is pretty straightforward. There's not a whole lot that's going on here. The only thing we could do is we could, you know, we could know these offsets ahead of time potentially, right? So that we don't have to do additional adds here. But the compiler is going to probably fold most of that stuff out, and so just looking at it this way is totally fine for now. We have those unpacks and the sRGBs to linears in here that we need to do, and then we have to unpack these lerps. So I'm going to start with the lerps. Since those are pretty basic. So the lerps, let's see, we've got to do 2 lerps, and then we have to lerp the result of the lerps, right? Again, this is pretty beastly. But I want to go through this at least once this way so you can see it. All right. So to do this, we've got to actually produce an intermediate value here, right? This is sort of like a, I don't know what we'll call this. You know, I guess, you know, we could even think about what that actually means multiplied out, though. So if you think about this in floating point, I mean, sorry, in non-vector form, in scalar, right? If you think of what that actually looks like, we're doing this operation on each one, right? If that makes sense. So it's basically, you know, it's this operation on each one. And, you know, we know that the lerp operation is going to be 1 minus fy times the first part, right? And then fy times the second part, like so. I'm gonna make this a little easier to read here. Right, so we know we're doing that operation, and then each of these lerps, we know that that's the exact same lerp, right? So I can replace this lerp with the same thing, 1.0 minus fx times texel A plus fx times texel B, like so, right? So yeah, I'm going to introduce, just to make this a little easier too, I'm going to make an ifx, which is basically just 1.0 minus that fx, and an ify, which is 1.0 minus fy, which are the pre-subtracted versions of these, just so we can look at them a little easier, right? So it's just ify times this expression, right? In fact, I guess I don't actually need another thing there. Fy times this expression, fx texel D, right? And at the end, it turns out to not be quite so nasty when we actually multiply it out. And furthermore, if we wanted to, we could actually pre-compute these blend terms more explicitly, right? Because using distributive property, right, I can just go ahead and multiply ify times both of these guys, right? Makes sense. And get rid of the parentheses. And then I can do the same thing here if I want to, right? Again, distribute fy out there. And now, if you actually look at these, we actually just have sort of 3 blend coefficients that do that whole lerp process already pre-multiplied out, right? We've basically got, like, you know, L0, L1, L2, L3, which are just these coefficients, right? There's L0, there's L1, there's L2, and there's L3, right? Oops, got to actually write it in there. And so what you can see is this whole bilinear blend just kind of folds down after you actually look at what it's doing. That whole blend just folds down into 4 multiplies and 4 adds, right? Because if I pre-compute the terms, I can then use those for everything that I actually need to do. Each one of the scalars can just actually have that happen to it directly, right? I can compute R, G, B, and A all exactly the same way without actually having to do that sort of lerp nesting ridiculousness, right? And off you go. So yeah, pretty straightforward, right? Seems pretty simple. You could even save a little bit more here by actually pre-multiplying the color in, I suppose, to these actual blend coefficients. I don't know if we actually want to go that far, but you can see that we're about to take this entire expression and multiply it by these. So we could instead multiply the 4 coefficients by these, right, and eliminate this, which would actually, but, well, it doesn't really help because it's still 4 multiplies, I guess. So, yeah, I guess that just moves it around, doesn't actually do anything for us. If we were going to use these more often, I suppose it would, but it looks like that's redundant, so we'll leave it the way it is. Okay, so there we go. Let's make sure that our lerp is still working at all. There we go. All looks pretty good. It's kind of hard to see. I wonder if we maybe should, yeah, get some stuff that's a little closer. But that's looking pretty good. Everything looks good. So there we go. All right, so we've got our bilinear blend. I might start putting some notes in here, which is like, this is the bilinear texture blend, just so we can see what's actually happening there, like so. And so then we still have that sRGB to linear and the unpacks. And then let's see, this is modulate by color, modulate by incoming color. This is clamp colors, valid range. This is load destination. And yeah, everything else looks about good. This is destination blend and repack. All right, so you can kind of start to see the stages in here now. We have to do this sRGB to linear and this unpack still, but then we are, after that, we have completely flattened this routine out to look at exactly what it actually does. So that there's no kind of mystery in there anymore. We flattened it down, and we can kind of look for any additional things in there that are maybe not necessarily needing to happen. But let's go ahead and just finish that off. So sRGB to linear, right? This has to unpack each of these texels. I don't think there's very much we can actually do to make this work any better than it actually does, unfortunately. But basically, if we are to take each of these guys here, just texel A, texel A, texel A, texel A, like so, and then we just modify it in place, that. I think that's basically what we're looking at. Yeah. So we got to do that 4 times. And oops, that's no good. All right. So now, last thing is the unpack. Everything still looks good. Last thing is our unpack. Our unpack looks like this. So there it is, right? Again, this guy is going to be float. We'll convert that over to float, and that'll just look like this, right? So that's actually doing texel A, just unpack sample A, right? So sample A, oops, sample A, like so. And texel BR, texel CR, and texel, oh wait, that's not what I wanted. AG, AB, AA. Okay, so that unpacks sample A, and we need to do that for each of our things. Like I said, unfortunately, got to do a bunch of unpacks here. Okay, C and B. And I think that concludes our flattening. And you can see there's quite a lot of code in here that has to actually run, which is a bummer, but it's why things are slow, right? If you've got a lot of code, that's a lot of code operating on a lot of things equals a slow program, to say the very least. Oops, typo there. There we go. And okay, so these are actually the guys doing the blend. There we go. Okay. Now, all right. So that's everything. I'm not sure if there's anything that we want to try to squeeze out of here that's actually happening before we go, but you can see, you know, yeah, it's big, but it's not that big. So at the end of the day, this isn't too awful, right? This isn't the worst that you're likely to see in your programming. And what's kind of funny, you know, I don't know what to say about this sort of stuff other than just, yeah, this is how it goes. You'll notice we're compiling with optimizations on, right? So if I go into the build, right, we've got -02, which says Microsoft C compiler, please optimize this as much as you want. So basically, none of that stuff that I did should have actually sped up the program at all. the only thing that would have sped it up was eliminating that code that was the normal map code. But as we saw, like each time as I've been going here, we've been getting faster and faster. All of those changes that I did actually sped the code up. Not nearly as much as we wanted to speed the code up, but it's just kind of silly, you know, these sort of, you know, just rigid transformations. Compilers just have a hard go of it, you know? It's a hard problem compiling optimized code, it is. And so it turns out that if you structure things a little clearer and you remove terms that maybe you think the compiler should have, it ends up being beneficial even before you actually optimize anything, because we really haven't done much that the compiler couldn't have done itself. We did the UV transformation and the remove the neural map code, about the only two things that the compiler couldn't have done itself probably, but you know, what are you gonna do? All right. So we don't have a lot of time left. We got, you know, 15 minutes left or something like that. But what I'd like you to take a look at now is, again, like I said, we want to sort of you know, have some kind of an opinion, try to get to a place where we have an idea of how much time this code is going to take to run, right? And a little bit of it's kind of hard for us to estimate, because packing and unpacking doesn't look like it looks in when we actually go to do the SIMD version of it. Some things look exactly the same. Like multiplies look like multiplies in SIMD. So you know, we can just look at the code and say, do we need to do a multiply? If the answer is yes, then that would have turned into a SIMD multiply when we go to optimize it. But some of the other things like pack and unpack actually look quite different depending on whether you're doing them in SIMD or not. And so stuff like this is a little bit harder. But that kind of gets to one of the things that I wanted to talk about, which is a little more complicated. And that is, really at the end of the day, if you take a look at how this code works and think about how we're going to SIMDize it, right? If you think about how we're going to start operating on this thing wide, we actually have kind of a really nasty problem with these unpackings that we do, right? And the reason that we have a kind of nasty problem with the unpackings is because if you look at everything else we do, everything we do in scalar form could easily be blown out to do 4 pixels at a time, right? You know, anything that we do that's just a regular operation like this could just be done on 4 pixels at the same time. It doesn't have any particular, you know, need to do anything else, right? But our unpack operations are actually not that way. Because if you look at what our unpack operations are, our unpack operations load a single value, right? They load like this one 32-bit integer. And then it has to convert that 32-bit integer out into separate channels, right? So you can see here, we're reading from the same value in a bunch of places and doing this sort of conversion out, which sort of, it's a little bit nasty, right? And you can see us, again, doing it here, like this combines a bunch of these things together to write a single thing out, right? And so we kind of have a choice that we have to make at some point. And I think maybe now would probably be a good time to start talking about it. I don't know if we want to, I want to kind of set the stage maybe for tomorrow, where we'll maybe talk about it in a little more detail. But basically the problem looks like this, right? What is our wide strategy, right? So what I talked about on the episode when I was sort of introducing optimization concepts is I talked a lot about this thing called SIMD, which is single instruction, multiple data, right? And what that meant is I said we were essentially going to have to start thinking about operating on 4 things at once, okay? Now, 4 things at once could mean multiple things, right? If I know that I'm going to operate on 4 floating point values, right? 0, 1, 2, 3. Well, what do those values mean? I could be talking about pixel 1, pixel 2, pixel 3, pixel 4, whatever, right? I could be talking about multiple pixels. So each one of my lanes, each one of my SIMD lanes could be a separate pixel. So I try to operate on 4 pixels at a time, let's say. That's one way. Another way to do it would be to map those to R, G, B, and A, right? So I basically have each of those mapped that way. And so when you think about how you want to operate on these, you have to kind of consider when you're operating on 4 things at once, what are the 4 things, right? What are they? And if you take a look at how things are working in here, you can see why one thing that we probably don't want to do is to use the format where it's RGBA, right? So if we were to talk about a SIMD architecture that was RGB and A packed into our SIMD registers, right? You can see already that that would be kind of bad because just looking at the operations we do, they don't chain that way very well. Most operations treat the alpha differently than they treat the RG and B, right? And so we'd constantly be fighting this situation where we gotta deal with the alpha in a different way, and we constantly be losing like a quarter of our performance by downshifting all the time to deal with it that way. So what we'd rather do is always be able to do it in something where the stuff happens exactly the same every time, and that's why pixels is a much more compelling thing, is because all of these things, if we were to do 4 pixels at a time, obviously all of these operations just work, whatever they are. If you're doing this operation, well, you're doing it on the A channel of 4 pixels at once, and you're just doing the same operation on all 4, right? Which is fine. But the same thing I just said about RGB turns out to be true when you look at unpacking, right? Unpacking is a problem because unpacking means that I can't just take some input values and then start working with them, right? I mean, the classic example for would be the RG and B's here, right? I load in, let's say I load in 4 pixel values, right? And they're 32-bit packed, right? So, this is RGBA here, RGBA here, RGBA here, GBA here. Because remember, each one of these things is 32 bits, right? And this is, excuse me, 128 bits long, right? It's one of these wide things. And normally we've got floats in there, but if we were to talk about looking at like the frame buffer or something like that, or the texture, they're these packed RGBA things, right? So when we load those in, we then have this nasty problem of we have to get from this, right, into something where we actually group all of the R's together, right? So we have to grab all the R's out, and then we have to grab all the G's out, right, to produce our R, our G, our B, and our A, so that we can start working on things in that pixel way, right? So, one thing that often happens when you're talking about really optimizing for stuff like this is you might convert your frame buffer format so that your frame buffer format is actually, instead of storing things this way, it actually just stores R's together, G's together, B's together, and so on, to save this annoying process that I'm showing you here, where I have to grab out certain things from every value. So I guess what I would say is about that, we're going to talk a bunch tomorrow about SIMD, because tomorrow is sort of the day that, we got our stuff flattened out here, and before we talk about how much each of these operations costs, I want to talk about SIMD a little so that everyone kind of understands what it is. And we've mentioned it a bunch of times, but I wanted to spend a good Blackboard session just talking about SIMD, how it works, what it means, and that sort of stuff, and so that we can go through and estimate the costs here. What I wanted to say about that is, because the goal for this is not to ship a software rasterizer, but rather to write a software rasterizer that works the same way GPUs generally work, because I think that's more educational and more interesting, since there's no point in shipping a software rasterizer in today's day and age. You're going to use the GPU if you want performance, right? I think we're not going to take that step of reorganizing our textures and our frame buffers to be packed R, packed G, packed B, and so on, because I'd rather do closer to what the GPU does, and the GPU does do that, does pack them. The GPU doesn't reorganize them. And the reason for that is that the GPU has much more powerful unpacking stuff that it can do. And it would rather have the cache locality of making sure, because it knows it's always going to use RGB and A's together. So it would rather have that cache locality. So instead, it just has hardware that does that unpacking very efficiently, right, and doesn't have to worry about it. We don't have that special purpose hardware on a CPU because they didn't put in instructions for doing that sort of unpacking. But the unpacking is not that bad. And so we'll see when we talk about SIMD tomorrow. There'll be ways that we can do the unpack probably relatively quickly. But it might be a little less efficient than it would have been if we had reorganized our frame buffer. All right, so anyway, we've got ourselves reorganized here, and we're about done with today's episode, so that's good. What I would like to do potentially here is, we haven't, one thing that we might want to do, I'm just trying to look and see if there's anything we need to kind of solidify. I don't think so. Basically, like pixel centers up here, the thing that determines whether or not you're touching a pixel explicitly or not, and how you convert from that to a texture coordinate, might be something we want to make a little more solid and a little more specified. But everything else pretty much is the same after that. And all of this code we've already vetted. Like this already is pretty much what we want to do. It does the operations in the right space. It produces the proper results that we want it to produce already. And so given that that's the case, I think we can go ahead and optimize just this whole part. And if later on when we go in, maybe we'll do a little pass to do some correctness stuff. If we have to change just the preamble part to pick the pixels in a slightly different way, that doesn't really bother me at all. So I think we're good. So I think that's a good place to leave it for today. Tomorrow we'll talk about what is exactly all the SIMD stuff is that we've been referring to and what instructions we have to work with there so that we can go through and make an estimate of how we're going to do all these things and how fast it should run. And then we just go ahead and convert it. Really. It's not that much more complicated than that, to be honest with you. That's honestly, that's it. It's pretty simple. So if we take a look at all this stuff, again, I hope that hasn't frightened you away too much, because really just the flattening down was just so we could make sure we see everything that has to happen and we know that we can do the steps in SIMD. And the reason I didn't blow out this clamp function also was because clamp is really a very specific thing that's very easy to do in SIMD. It doesn't require branching. So it would be very misleading if I blew out the scalar version of these with the ifs and stuff like that. Basically, that's why that is the way that is. So clamp will really just translate to 2 instructions in SIMD, so I didn't feel like it was necessary to extract that out because it would be very, very straightforward. But yeah, so let's go ahead and go to the Q&A. And if anyone has any questions, I will take them now. Brain Cruiser, the way the code is written now, you have a very long dependency chain between instructions. Will you break down the code to remove it? There really isn't a dependency chain here for an Intel processor. So if you take a look at this, right, we've got unpacking issues aside, right? If you take a look at these, any given window here of instructions, there's tons of things that are not dependent, right? For example, it can issue all 4 of these totally separately, right? This does not depend on this, does not depend on this, does not depend on this, right? And so as long as you have enough instructions to mask whatever the latency is of a particular unit, or the throughput is of a particular, whatever the latency is of the particular unit you're targeting, right? So let's say you're doing multiplies or whatever. As long as you have enough so that you can, that it will retire in time, you're totally fine, right? So it could issue, for example, these 2 multiplies together, and then this one and this one. It could issue all of those together, and by the time it's issued 4 of those and comes back to issue the next ones, you're probably okay, right? And similarly, even if it can't, like let's say it issues these all, and then it can't do the square yet because it's waiting for this, it can issue all of these because these are all independent. It can issue all of these because these are all independent, right? And the window's pretty large, so, again, rearranging these is not necessarily all that valuable for you to do, if that makes sense. But if it's something that you're worried about, you can certainly do this, right? You can certainly start pushing things up more together, or you can pull the multiplies out so that you do the square down here as a separate thing. I'm not sure that there's really any point in doing any of that, because there's really just not that much serial dependency here in terms of the actual window that the processor is going to look at, if that makes sense. But yeah. The other problem that we do have, though, a little bit, is that there's nothing you can do about the fact that things are a little serially dependent. It's pixel processing, so you gotta, you have some serial dependencies there. But I don't think, basically, the processors are very fast with how fast multiplies move through the pipeline. The latency isn't 300 cycles. It's like 8 cycles or 6 cycles or whatever, right? And so you really don't have to have that many instructions in the window for that to work. Stellar 7. Why did I write float instead of real 32? Thank you for catching that. There's a very specific reason why I wrote that. Something that annoys me to no end, but I'm almost coming to the end of it now, so it's fine. I had to do a bunch of optimization work on the witness for the past 3 days, and in there it's called float, right? So I had to get used to typing float for 3 days. Why did you use O2 instead of O3 or O fast? I think just because I don't really know the compiler switches these days that well. Is O3 faster than O2 by any? Let's find out. So let's see here. Here's our game running. We've got 240 some odd cycles happening per pixel there. Here's O3. It says ignoring unknown option. O fast. Are you sure these are actual switches? Stellar 7? Do you ever use exclusive OR operations to avoid pipeline stalls? If not, what do you use? No, I generally don't, because I don't tend to do that level of optimization. Like, generally, well, I shouldn't say that. Sometimes I do use exclusive OR, but I don't use them because I'm trying to avoid pipeline stalls. I use them because I'm programming in SIMD and you have to do a bunch of manipulation with tests and stuff like that. But basically, like, my optimization tends to just be I write stuff in SIMD. I lay it out and I write it in SIMD, and then I'm done, right? I usually do not go beyond that. Like I said, on the Xbox 360, I did a bunch of work where I did go beyond that because it was a very special circumstance. But that's not my normal modus operandi. Like, I am not the guy who uses exclusive OR to avoid a pipeline stall. Like, that's not the kind of optimization I tend to do. Aren't those square roots pretty expensive? So actually they're not. And that's pretty interesting. You can, I don't know if there's a good thing on here for that, but if you take a look in SSE2, right, you've got the, I just don't know if this guide has the some of the stuff in here. If you take a look in it, I don't actually want, I just want to see the square root routines. There it is. So if you take a look at the in square root PS routine here, right? This routine actually completes in a reasonable amount of time. This instruction actually completes in a reasonable amount of time, it is not slow instruction. And what is it on? I don't actually know. What is that blue? I don't know what the blue is supposed to be representing there. This is the one I actually wanted. Oh, here it is. Reciprocal square root. That's the one I actually wanted. So getting 1 over the square root, right? Which is pretty crazy, right? 1 over the square root is actually crazy fast. You can actually do 1 over the square root in hardly any time at all. Like, take a look at this. Latency 5, throughput 1, and it goes down all the way down to latency to 3 if you're on the other one, right? But on any of the modern cores, it's a bit of latency, but you can issue a ton of them, right? So you can actually, if you're issuing several of them, you can actually get them going through at 1 cycle per inverse square root. And so since we don't actually care that much about how accurate the square roots are, I would suppose that we're going to be able to do those pretty quickly. You know, it's an inverse square root, so we'll have to do, I don't think we have access to the regular square root. I don't actually remember if whether the regular square root is actually in there or not. Let's see here. I think they added that later. I'm sorry, I've never used this. This was something that someone on the stream pointed out to me. It's pretty cool, but I've never used it before, so I'm kind of lame at actually finding it. So I feel like there should be a square root that was actually on here. I feel like they added square root at some point, right? I mean, pretty sure squirt PD, but where is squirt PS? Well, tell you what. squirt PS, there it is. Yeah. So here, if we actually just want to do the regular square root, instead of doing like a thing in an inversion, even then, it's not that bad, right? It gets worse if we go down, but that's not that bad. And that's actually available on regular SSE, I guess. So that's been in there forever. So doing the square root, yeah, I mean, do we want to have to spend 14 cycles or 7 cycles, depending on the processor? You know, no. But at the same time, it's like, well, you know, it's not too bad, and we can do the accurate rendering. Now, if we want to, we can always just get rid of these, because all they were is to do light linear computations, right? So if we find they're too slow and we really want to get rid of them, we can, but that's not too bad. So I think we could probably do it. For example, you know, one way we could do it is, you know, we have some overhead for doing this throughput. We could probably do that and try to like mask out some, you know, try to basically like have some other stuff going on while that's happening. So maybe it overlaps particularly nicely. I'm not sure, but I think it should be pretty good. I think it's not too bad. It will definitely be one of the more expensive instructions that we ever call, though. That's definitely true. Will you make multiple SIMD backends? No, we're only going to do one SIMD backend because really the other SIMD backends would just be kind of they're just not that interesting. They'd just be wider, right? Because we're not using that many fancy instructions, so it's not. I guess maybe with the unpacking, there's some things we could do differently, but I don't think it's worth it since we're not trying to ship the renderer as a thing that people will actually use. I don't know that there's much point in doing multiple SIMD backends. You could loft some of those variables out one more loop. Yes, that's probably true. We could. I haven't looked too much at which ones we would loft out, though. I don't think there's that many. You know, like some of these can be moved. But the compiler will almost definitely do those. But yeah, you know, we can take a look. I didn't want to do, the reason I didn't do these two was because we want to talk about this a little bit, because we still haven't sort of decided exactly how that multiplication happens. But yeah. I think this is actually wrong. I think this should be -1. Yeah. How expensive is the float to int conversion compared to the rest of the workload? I think it typically takes about 2 cycles. It's an SSE instruction. It's called convert. You can take a look at it here. So basically, like, you know, here's what you're looking at. So I guess you can actually, it only takes 1 cycle to do that conversion. So it's pretty painless. It used to be the case that it was nasty, but it's pretty painless now. Since x-axis and y-axis are usually perpendicular, should we special case for that? In the same vein, should we special case for axis aligned? So I don't know that there's really all that much we have to do to special case, because if you look at this, I mean, just look at this. All of this work is what we have to do per pixel. So saving the special case for the axis alignedness is just not that interesting. The way that it might be, the place that it would be beneficial would be the texture lookups, because you could reuse some of them. But again, I want to keep this relatively close to how the GPU works, so I don't really know if I want to go down that road too much. And plus, since it's going to be in the cache when you do those multiple fetches, I don't know that you would save that much anyway. But yeah, if you wanted to go as fast as possible, you would probably special case basically axis aligned so that you could optimize your texture fetches to reuse textiles you've already had. And you'd probably do both. You do a shrinking one and a growing one separately. Does the compiler do any automatic SSE optimization? I think so. I don't think it probably did it for us, but I think it does. On LLVM, it definitely has a vectorizer you can invoke, but I don't really know about Visual Studios. I pretty much always write it myself, so I don't really know. Let me see if I can get this to happen here. So if we take a look at what it's doing, go to disassembly, we can kind of look to see if it looks like it's doing anything particularly intelligent with that. I don't actually know if it is or not, but let's see. XOR, there we go. Where is my, there is the registers. Let's take a look at the SSE registers. There we go. So you can kind of see, unfortunately, the answer is no, it really hasn't done anything. It's pretty much working exclusively in just the lower part of the register, right? Because this is the register. And you know, if it was operating on a bunch of things at once, you would see it spread out in here. And so you can kind of see that it's just doing everything in scalar and keeping it in the lower part of the SSE register. So it's never actually doing anything out here. So it didn't happen to in this case. I don't know. There might be some feature you can turn on, but I'm not sure. Squirt SS versus Squirt PS versus Squirt PD. Okay, so this is just the ridiculous. We'll talk a little bit about this tomorrow. And it always confuses me to no end anyway. But for whatever reason, when they introduced these intrinsics, you know, they're _mm. I think that might have stood for multimedia or something. I don't even know. Don't ask me. But anyway, the way that they chose to name them is like, you know, it's mm, _mm, and then it's underscore whatever the thing is that you're trying to do, right? So like, you know, if you're trying to do a square root, it's going to be squirt in the middle. So the operation goes in the middle. And then the suffix is like what kind of thing it's actually, like how it's treating the stuff in the register. So PD means packed doubles. So basically that's going to operate on 2 doubles. You can kind of see it here, right? It's going to do 2 64-bit square roots. Whereas PS is packed singles, right? So that's going to be 4 32-bit floating point values. And you can see that happening in here. And then SS means I only actually needed to do one of them, right? And so it's actually doing it on that lower, just the 32-bit, the low 32-bit one. I don't know. Yeah, so it looks like this also does a broadcast, right? Pre-packed elements from A. Oh no, it doesn't. It also, so this does, it does the square root in the bottom, and then it leaves the upper 3. It like passes the upper 3 through for you, for whatever reason. So this only does one of them, right? And so that's why there's a PS, a PD, and an SS. It gets even worse. You didn't see these, but if you have other operations like add that apply to everything, you also have all of these. EPI 16, 32, 64, and 8. Those are basically talking about doing an add on 8 16-bit values in integer. So EPI is like the integer. It's saying integer, 16 wide. And of course, you can fit 8 of those in 128 bits. There you go. This is 4 packed 32-bit integers. This is 2 packed 64-bit integers. This is 16 packed 8-bit integers, and so on, right? So yeah, I think the E versus the P is just to distinguish it between when they had just MMX that was only 64 bits wide instead of 128 bits wide. But yeah, it's I mean, it's a mess. You know, it is actually a fairly consistent naming scheme, but it's a mess. Would SSE allow doing sRGB using exponent 2.2 instead of approximating using 1, instead of approximating using 2, without a huge performance hit? No, actually. I mean, it's not a huge performance hit, but it is definitely a performance hit. It requires a table. It's nasty. Raising something to the 2.2 power is really hard. And so the difference between square rooting versus doing the raise to 2.2 and raising to the 2.2 is a pretty massive difference, actually. It doesn't matter whether you're an SSE or not. It doesn't get easier. The main reason why you don't get automatic SIMD is precise exceptions. You probably need to tell the compiler that you don't need them. Yeah, so what pseudonym 73 is talking about is the fact that, and there's actually a couple things like this, which is that the C specification and the IEEE specification, there's a bunch of things that generally have to happen that the compiler has to obey when it's doing floating point operations. And if you don't allow it some latitude, it might not be able to do basically all of the optimizations it could do, right? And so there's flags that maybe turn those off the compiler. Like I said, I'm not super familiar with them, so I'm not sure exactly what they would be. Pseudonym 73 was talking about precise exceptions. There's another one called floating point consistency, which has to do with the order of operations that restricts what the compiler can do. So there are ways you can try to tell the compiler, be lenient, and then it will, you know, maybe do those for you. Now we are saying -FP fast already, but I'm not sure if there's additional ones that try to tell it, you know, that you don't need like things like precise exceptions. Let me see if there's any documentation for that. So except minus might be useful. Let's see. So let's try it. We can try adding there, but I don't actually know if that's gonna help us too much, but we can certainly try it. All right. So if I go ahead and set a breakpoint in here and take a look, still no, right? Still definitely not using any more of the width. But I don't necessarily blame it. I mean, you know, I don't expect it to auto-vectorize my code. I can vectorize my code. What happens if Arch AVX2 switch is enabled? I don't know. First of all, this machine would crash because it doesn't have AVX2. In fact, this machine doesn't even have AVX1. I think this machine only has SSE3 or something. Maybe SSE4, I'm not sure. But I'm pretty sure it doesn't have AVX2. In fact, no, machines, I guess it's AVX512 that machines don't have right now. And by the way, I looked at this the other day. This is crazy. Has anyone done this? Like, look at this. I don't even know. I gotta learn this stuff eventually. I don't even know. Like, what is AVX512 IFMA? I literally don't even know what that means. Like, I have no idea what these subcategories are. Because normally when you go in here, right, and you look at these, there's just, you know, there's just the instructions for that grouping. So if you say I'm SSE 4.2, it's like these were the things they had in SSE 4.2. But AVX 512, what is this? I'd never seen this before. So they've like broken down the instructions into some other bunch of are these actually different caps bits that the processor would have? And if so, who is in charge? That's ridiculous. I sure hope that's not true, because who is going to actually check to see which of these combinations you would have and whether to run them? So I don't even know. I hope that's not what that is, because that would be crazy if that were the case. But yeah. So yeah. FMA is fused, multiply, add. Well, sure. I mean, yes, FMA is fused, multiply, but FMA is not the weird one, right? FMA is a separate thing that you can select on and off here, right? It's AVX512 that drops down all of this stuff, and I have no idea what all that is. So sure, there's like an IFMA52, and probably that has something to do with fuse, multiply, add, but what does the rest of it mean? And is it a caps bit? I don't know, right? So that is the thing that's weird, not like what is FMA or whatever, you know? All of that said, a lot of these I don't even know what they might mean. Like, I don't know what a DQ would stand for either, and so on. But point being, so I don't know, like, I don't know what any of this stuff actually means. I don't know if, like, you know, I don't know, for example, if this is a caps bit, you would have to check on the processor. And then, you know, if it had it, then you could issue MAD 52 high, right? And if it didn't, you couldn't or something. Because that's just crazy if that's true. So I don't know what that means. I hope that's not what that means. That's what the rest of these mean, right? Like normally if I click on SSE3, this shows me the stuff that the SSE3 caps bit would tell me if it had, right? And caps bit's not really the right term, but if I check the CPU ID and I know it has SSE3, I can call these. That's how that works, right? But I just don't understand what this means, because I don't know what it means. So I got to go read like the architecture reference manual and find out what all of this meant. Since AVX 512 isn't out yet, I haven't bothered to research how that works, but yeah, it's just kind of crazy is all. Oh man, Andy SZ says, yeah, it looks like different caps bits. Oh, I mean, just think it, just that's horrible. Like, why would you do that? I mean, basically at that point, you're basically just saying, I'm targeting scientific computing, right? Because no one's going to ship a commercial product that actually uses random combinations of these things and falls back to different paths or something. It'd be insane, right? It's just too much. So that's just crazy. I wish they wouldn't do that. That's just not cool. Oh well. Anyway. All right. Let's go ahead and wrap things up. Casey is hungry and wants to eat dinner. So let's go ahead and close this stuff down. There we go. Minimize you. All right. Thanks everyone for joining me for another episode of Handmade Hero. I hope you'll come back again tomorrow. And I think, I'm just going to give you fair warning, I think tomorrow may end up getting moved to 9 a.m. I'm going to go look at it now, and I may have to do that because basically, for those of you who know Jeff, he is he is having to well, I won't go into too much detail, but anyway, for those of you who know Jeff, he is going to have to go have some surgery tomorrow, and I wanted to go visit him tomorrow evening, and the stream would have overlapped when that would have happened. So I think I'm going to try and move the stream so that I can go to that. And for those of you who know Jeff, please wish him well and wish him a speedy recovery. Not that you can anymore, because he's basically removed himself from the internet. But yeah, suffice to say, I'm going to probably move the stream for that. So I apologize for the last minute notice, but it was kind of a last minute thing. And so I will probably update the Handmade Hero schedule to move it to 9 a.m. tomorrow. So we'll do 9 a.m. both days, both Thursday and Friday. So thanks everyone for joining me for Handmade Hero. Hopefully come back tomorrow. Like I said, probably it'll be 9 a.m. tomorrow, even though originally I said it was 5. I'm probably gonna have to move it. So we'll do that. And tomorrow what we'll do is we'll talk about SIMD, basically how SIMD instructions work, how we write them, how we get the compiler to compile them and do them, right? We'll talk about how to make that happen, and hopefully we'll have some time tomorrow to actually start writing some of that. We probably won't finish, because by the time I explain how everything works, we probably won't have enough time. But between tomorrow and Friday, we probably should, I think, be able to get a fairly reasonable SIMD version of our thing in place so that we can take a look at that and figure out how fast we think we should be able to get it to run when we, at the limit, right? And again, like I said, that's a pretty important thing to want to do, because one of the problems with optimizing stuff is you kind of have to go, if you don't go through and count how many cycles you think something can run at peak, there's not a lot of ways to know how much performance you're losing from other things that are interfering, like cache stalls, this sort of thing. And so that's basically what we're going to be doing. So hopefully come back tomorrow 9 a.m. to join me for that. Until then, if you do want to follow along at home and you want to pre-order the game on handmadehero.org, you can do so. Just go ahead and do that. You'll get a link that allows you to download the source code so you can follow along. We also have a forum site. You can go to post questions and that sort of stuff. It's also got ports to Mac and Linux if you're interested in that. And there's also an annotated episode guide and other kinds of good resources there. We have a Patreon page if you want to support the video series. If you'd like to subscribe to that, that's always very much appreciated. And we also have a tweet bot that tweets a schedule at you for exactly the kind of situation I was just talking about, where if there's something like a medical emergency or things like this, and I have to move the stream, and you don't want to be sitting around going, where is Handmade Hero? That is the best place to get those updates, because I try to keep the Twitter stream pretty up to date as much as I can, so that you always know what's going on with the stream and don't have to wait for Twitch to tell you that it's on or not. So check that out. Until tomorrow, everyone, please have a fabulous coding day, and hopefully I'll see you back here again, like I said, probably 9 a.m., but check the Twitter. I will post definitively tonight. Take it easy, everyone.